like shootings.
Okay, great. So I've ended the third problem sheet. I think everyone has a copy. Tell me if you need more for friends or whatever. Friends that are not doing this course. Hey, puzzles for you.
Problem sheet?
Yeah. Want to do them? Okay, so just to put you in context, well, please, I want feedback if some of the questions make nonsense. Perhaps it would be good if you read them somewhat quickly, because I suggested, well, as a return date, it's going to be not this Thursday, but the following Thursday. So that gives you 9 days. Let's touch base next Thursday, well, this week on Thursday, to make sure all the questions are well defined and neat and you understand them. Now, I also, well, one suggestion is to start working on them somewhat early, because sometimes you get stuck. That's completely normal. It's the part of the fun of it. And then it'd be good if we can, discuss among yourselves, and even don't hesitate to ask questions. I'm happy to help. We can also take appointments. Just write me an email and we can meet each other to discuss the problems. But for example, in question 4, I put some hints. So if I were to solve that question the day before I need to hand the solution and go like, what this hint is about, there's chances I won't find it. But if you hit the first wall and then you're like, oh yeah, what's this hint about? And then maybe you discuss with your fellows, like, hey, have you done some analysis in mathematics? Like, what happens with series or whatever? And how can this be useful? And then you brainstorm. Eventually the hint's going to make sense. That's what I mean. It's just sometimes, like, when we're rushed, the hint is not going to make sense. Now, I had in mind, like, one question I thought was really hard, so I wanted to put it as a bonus. Like, you don't have to do anything anyways, but, there's no points specifically for that question, but I was happy to give more points if you give me a solution. But then I realized that I'm extremely biased, and I'm not the good person to assess which question is difficult and which is not. So arguably, it might have been another question which was most difficult. So I decided to leave the bonus very open. Basically, like, that's my note number 1. If you provide 7 good solutions, you'll get 70 out of 60. So any question can be qualified as the bonus question. You can also choose your 6 favorite questions and give me 6 solutions. You can still get them, 60 out of 60 if you do that. Yeah, I'm really curious to get some of your feedback on those questions. So question 4 was hard. I thought it was really, really hard. And then I gave 2 hints. And with these 2 hints, it's sort of killing away some of its hardness. So maybe question 6 is the hardest. Maybe it's question 5. You'll tell me. I'm really curious to know. We're almost. Let's view them one by one. Question 1 is the string 0n. This was 0, 0, 0, 0 n times. And I asked you to show that the plane complexity of that string is the same as the plane complexity of n. I have used that fact in one of the courses, the course we were in that room. I've used that, and I gave a super brief argument, but this is like somewhat an easy question just to make sure you're, how do we show these things, right? Just to make it explicit, there's 2 things you should show. Because when you have an equality with O of 1 quantity, you have to show that, it's smaller or equal, the left-hand side is smaller or equal than the right-hand side plus O of 1. Yeah, and then the other way around. The right-hand side is smaller or equal to the left-hand side plus O of 1. Now, question 2 is somewhat similar, but that's motivated by Edita's question. He came to me and he said, what's the link between plane and prefix complexity? Are they close to one another? Well, then question 2 shows that they're logarithmically close. So, the fact that we've changed the setting to prefix complexity is not, doubling the Kolmogorov complexity, or it's adding an error term. The difference between the 2 is an error term, which is logarithmic in the length of the string x. So it's comparably very small, comparably with either k of x or c of x. Now, question 3 is no surprise. I told you we want to show them the easy side of the chain rule for prefix complexity. That's what it is. Question 4, I thought it was the hard one, and we'll come back to it today because it's extremely related to how we finished the course last time. Yeah, I'll come back to it in a second. Question 5, that's a tricky question for me to pose, but I think my hope in writing the question this way, so what's question 5? A is a finite set. Its cardinality is denoted some way, cardinality of A. Find an appropriate definition for k of A. And use that definition to show that for all string in A, k of x is smaller or equal than k of A plus the log of the cardinality of A plus O of 1 error term. Now, usually, I guess the pedestrian way of having posed the question would have been for me to give you a definition of the algorithmic complexity of a set. But my hope, with this course is to get you into a bit of a researcher's mindset and get into a mindset in which, it would be useful if we have this thing, the Kolmogorov complexity of a set. Well, then the natural thing to do when you're a researcher is to come up with ideas of how we could formalize it, how we could define it. So I wanted you to have those shoes for a minute. I'm sure if you Google it, you'll find solutions or you'll find proposals, but think of it for a minute. What could be, A is a finite set, what could be an appropriate definition of the algorithmic complexity of a set? And then there should be one definition for which you're going to be able to prove the relationship. Okay, so if you come up with a definition which doesn't enable you to prove the relationship, and then you find another definition which enables you to prove the relationship, well then write down the one that gets the job done, which is also what we do pragmatically in research. We might come up with various definitions to grasp a concept, and we use whichever work, basically. Okay, so again, provide feedback if you're lost. I know it might be the first time you're in this, scenario of coming up with definitions. How should I think about it? You know what? I think it's not really hard. We've seen, Kolmogorov complexity of a pair of strings. Now it's a set. There's details. Devil's in the details, and be precise in how you would want the definition to go. Now, question 6 is, you cannot really try it now, but we maybe after today or after Thursday for sure, you'll be good to tackle it. So I'll just skip it. And question 7, we're also going to see it in my introduction, basically. I define a concept. A function is upper semi-computable if, and I ask you to show that the Kolmogorov complexity function or the algorithmic complexity function is upper semi-computable. Okay, so please, 2 things. If there's a question that makes no sense, we've got some, there might be mistakes in the way I have phrased them, so please go ahead and reach out. And also, but more importantly, if you're stuck in problem solving them, write me an email or go for a coffee together with some colleagues and me, and we discuss that in the courtyard, whatever.
And number 4, you said you would come back to it?
Yeah, I'll come back to it in the
lecture.
Once I can write something down. Yeah.
See, hint 1 isn't, I'm not sure if it's incomplete or it's just really a hint, but it looks like it should say that equals something or is less than something. It just says a sum.
Yeah.
Okay, it's just to make you think.
It's an incomplete sentence, but
okay.
Yeah. How should I start this course? Yeah. In fact, I said we're going to come back to question 4 and to question 7. Very short. I think the logical and the pedagogical thing I should do is to start where we were last time, because we left something on the table, and then we will come back to the function k of x. So, where were we last time? There was an easy side and there was a hard side. There were two things we needed to show. One was in red and one was in green, I think. That was the easy side. O of 1, x star, then you get k of x and x.
Oh, also, are we recording?
Thanks for asking, we are. Yeah.
Nice.
I think this was the red star, wasn't it? No?
Yes.
Yes. This was the red equation. And we had the green equation, which is just the other way around. From k of x and x, you can feed that into a constant size computer program, and we're going to get x star. So this notation here, this was my green equation. Notation here is basically this is just a way to write that k of x and x given x star was equal to O of 1. Right? As I said, all the pieces of information that are written here are displayed in that figure. And what this equation says is that, well, the length of the shortest program to produce two things, k of x and x, given some auxiliary information x star, the shortest program for x, is O of 1. So there's a constant size program which can transform x star into x and k of x. And I elected to write it this way. I think it's more visual. There's a constant size program which can take auxiliary information x star and transform it into the output, well, an encoding of the pair of output x and k of x. Okay, so we said the red star was the easy one. Why? How can we show red?
Well, the explicit program is pretty easy to just read off. It's just first read the length of x star and output that. And that tells you k of x. And then compute x star.
There you go.
And it'll output x by definition.
Read the length of x star. Output that. Pardon me. And then execute x star. The output this will be k of x by definition, the length of x star. By executing x star, we get as an output x. So that's for the red equation. Now for the green, I think the green we left open. What was it? Anybody thought of a solution?
Yes.
So if you are given k of x and x, how can you produce x star?
Try all the strings of length k of x.
Yeah, and you'd have to dovetail.
The one that produces x, you output it.
How do I try them all?
Just for loop.
Yeah, but you want to dovetail, right? You'd want to take all the strings of length k of x, and then run them all for one step, and then run them all for another step, and so on. Because otherwise, if you just start running the first one, it could loop forever, and you'd never get to.
Ah, yeah. True.
Yeah, it's a good point. So Pasquale's original solution, I'm going to start by running the first string of length k of x, which is, for example, just zeros. And then see what it produces. I hope I'm looking for a candidate for producing x. And then I'm going to be, running the other one. And I'm going to check, does it produce x or not? And eventually, there's a promise. There's going to be one string of length k of x, namely, at least, it's going to be x star, which is going to produce x. And so I should find it this way. Now, what Will flagged, basically, he said, hang on, you might get stuck in a trap. I think I used those words when we saw Turing machines. It might be the case that this program never halts. And so if I'm just brute forcing, okay, let me try u of the first string of length k of x, well, I might get stuck in a trap. And it might never halt. So what's the trick? There's going to be, there is 2 to the k of x strings of length k of x. Computing the first one, regardless, is a dangerous idea, as I said, because it might be a looping computation. So Will's solution was to run them in parallel. Exactly. So there are okay, if you're writing notes, what I'm writing here might be misleading. Let me just say this is a trap. Because you might get stuck in a hole or in a trap. I can't remember what I said when we saw that for Turing machines. But the idea is that there are 2 to the k strings of length k of x. Run them all in parallel for I steps. And the idea is that we start I equals to 1, and then to 2, and then to 3, and so on. And we increase I. Right? We are given k of x. K of x is equal to some number. K of x is equal to some number. So we're running all strings of length k of x. And yeah, what's the idea? We run them in for I steps, and we're increasing I. This way, we never get stuck in a loop, in a hole. If this computation doesn't halt, it's all right. I'm going to be running it for I steps, then I'm going to increase I, but at least I'm going to be running them all. And I do that. Eventually, some p halt with u of p equals x. Output that p. It is x star. K of x is given. I run all possible strings, which I interpret those strings as possible programs. I run them on U, the universal self-delimiting Turing machine, and I check if it produces some output for which the output is x. It's guaranteed that this computation is going to work because of x star. X star is one string of length k of x, which produces x. And by the way, this is where we see that the definition works. I said when we have many shortest programs, we define x star as the first one that halt. So in this parallel running of all programs of length k of x, well, P, this first one that produces x star, that produces x, is going to be X star according to our definition.
Could you say what exactly is this machine runs in constant time of what? In the size of what?
It's not constant time. Okay. This is constant
Size of the program.
size
Yeah, I found that confusing too.
of the program.
So then we run all of these k of x size programs, and that's it. We don't dovetail up to k of x. We just dovetail at k of x, and that's it.
Exactly. The word dovetail typically is associated with running an unbounded number of programs
Yeah, just
for an unbounded number of steps. That's why I used parallel. Even though I don't have, many parallel machines, but I don't need to run an unbounded number of programs. I need to run 2 to the power of k of x programs. Namely, all those that have length k of x. What do? I run them all for 1 step. I run them all for 2 steps. I run them all for 3 steps. I run them all for 4 steps. Oh, I've got one program that has halted, but it has produced the string 0. The string 0 is not the string x. So I continue. I run all my programs for 5 steps. Eventually, I'll find x star.
in this situation, you kind of trust k of x, that input is actually the size of the shortest program.
Yeah. Here, I'm not really solving the problem of how is this given to you, who found that, right? I'm just saying, well, if you have this and this, and they fulfill the right definitions, there's no bluff. I mean, it really is k of x. It really is x. Then there's a constant size program. It might run for huge time. But I don't mind. It's a constant size program, which will transform it into x star. Or will be able to produce x star.
No, my question was about whether we actually need k of x. Because I could just start with all the strings of length 1 and then of length 2. And then I will eventually end up having a k of x. But then the problem is that this is actually equivalent to the halting problem, right?
You can bound it up to length of x. Because you can always say like print of x.
Yes, but the problem is that how can I be sure that some short string is actually not giving me x and it is or
It could be that extremely short program runs extremely long to produce.
exactly.
And we never know that.
If you're not given k of x, but you're trying this argument, you're gonna use dovetail. I was about to define dovetailing in this course. Let me just go orally first. I'm gonna run all programs of length I or less for I computational steps. And then you increase I. Once you found, eventually you want to find a program that produces X. Vincent nailed it. He said, you might find a program that produces X of length 1,500 bits. Is that the shortest program? You don't know. Because there's still some shorter program than 1,500 bits that have not yet terminated their computation. Maybe none of them produce X, in which case you really do have the witness for k of x. You really do have x star. But maybe some do. And if some do, how can you know? It could be that x star is the shortest program, but it runs for a time very, very large. And so, for example, the print x program will be faster.
So the only way you can know is if either all the shorter programs halt, like you run it long enough and you see all of them halt, and then you're like, okay, for sure this is the one. Or you can somehow prove that the ones that are not halting will never halt. Or that they will halt and spit out something else. but that's
Is that equivalent to your first point?
well, I mean, like, so it could be that, I don't know, program 6 is the shortest one that spits out X, and program 5 is shorter but will never halt. And then the only way I can be sure that 6 is the one is to prove that program 5 is not going to halt, but that's the halting problem all over again.
Yeah, exactly.
So really the only way is if all of them halt, if you're very, very lucky.
Yeah.
Also, if you go back to the definition of X star,
Yes.
that's the reason that we define X star to be if they have the same length. The fastest one, like the one finishes at the least steps, is X star
Yes.
because of that reason.
Because of that reason. Correct. Exactly. Right? Because this algorithm here is going to produce one shortest program, namely one program that produces X and has length K of X. But which one? The fastest one. The one that runs in the least amount of computational steps. And even if there's a tie there, then it boils down to the ordering of the strings that you
Because
can
we
take.
go with the order.
The lexicographical ordering you can take. But yeah, it defines a unique X star, which it produces a unique X star, which coincides precisely with the definition we gave of X star. Good remark. Questions? Okay. By the way, I wanted to clear this result that I think I phrased it by saying that X star and the pair of string X and K of X are informationally equivalent. From one you can compute the other, and from the other you can compute one. So that you might want to be writing the chain rule like this. K of xy is equal to K of x plus K of y, given not X star, but X and K of x plus O of 1. That's another way to write the chain rule. Right? Because if you have X star as a resource, you can get that instead as a resource. And if you have this pair as a resource, you can get X star as a resource.
With an O of 1 overhead, which gets absorbed into that O of 1.
Correct. Exactly. Cool. So here I come now to I wanted to do a recall of last time. The reason I cleared that is because I'm closing a parenthesis, and now the recall of last time is gonna smoothly continue with today's course. Let us try and draw a function x k of x. X is a string or it's a natural number. We don't mind. Let's understand it as a natural number. It might be easier. Last time we saw an upper bound. This function, I'll call it f of x. F of x was equal to, correct me if I'm wrong, I might get the number of log wrong, log x plus log x plus log x, I think we had this one, plus order of log for x, fourth iteration of the logarithm. Is that the upper bound we proved last time?
Didn't we prove it for all variants of those kind of nested logs? Because basically the more times you encode the length of a string, like the more you try to compress, you'll get more of these log terms. But basically, I mean, you could have also just done log x plus O1, right? Or
okay, no, so what I want to show is that k of x is smaller than f of x for all x. Okay, I'll have to.
Yeah, this is what we did.
This is what we proved. Okay, thanks. I think I finished because we had like a sort of a fun conversation, and I finished with a bound that is tighter that involved log star. But
did log k.
Yes.
Said after a while, it goes to the negative. So
Yes, there you go. Yeah, we sort of had that conversation, but I didn't prove this last fact. What I proved is this one by reusing the bound several times. So yeah, we had that. Okay, good. Because I want to get to question 4 of the problem. Now, in question 4 of the problem sheet, are you David?
Yeah.
Nice to meet you.
thank you.
So, okay, yeah, perfect. In question 4, we have this function here. Let me call it g of x. Log x plus log x plus log x. And no error term, no extra contribution of order the 4th iteration of the logarithm. So it's technically a little smaller. Last time we showed that for all x, k of x is smaller or equal to f of x. So the red line is an upper bound for the algorithmic complexity. Now, why did I draw it like that? Well, it's essentially the logarithmic function, right? The log is already extremely small compared to log. So I essentially drew it as a logarithmic function. And I'm being extremely generous in the gap that I put between my red function and my blue function, because that gap is order of log x, super small. So the algorithmic complexity as a function might look like this. I never made it exceed the red line. I made it exceed the blue line. The reason why I never made it exceed the red line is because of what we showed last time. And the reason why I made it exceed the blue line is because of question 4. This what brings me now to question 4, where I ask you to show that there exists infinitely many x such that, I'll even write it down. Question 4, there exists infinitely many x such that k of x is larger than log x plus log x plus log x. And so the amount of times that, well, the number of points for which the function k of x, which is my black curve, is exceeding the blue line is infinite. There's infinitely many points that exceed the blue line.
X again should be intended as the length of the string, right?
No. Here x is the string.
Oh, right. Yeah, the binary encoding of the string.
Yeah. So I'm really viewing k here as a function, if you want. That's what I'm studying here. Now, why did I do that? Why did I make it drop like that?
There are a lot of zeros there.
Yeah, there are plenty of strings that are simple, right? Maybe this x, I don't know, maybe it's 2 to the 2 to the 10. It's a large number. I'm very far on the axis here, but that's a simple number. Its algorithmic complexity is going to be low compared to the size here. So the graph has to drop. You know, it drops for every power of 2. Every power of 2 is full of zeros. It's 1 with a ton of zeros. That's a simple string. But it drops even more when the power of 2 is also a power of 2. Like, and you know, we have seen those, I think, at one point I did, you know, the k iteration of the exponential to come up with compressible strings. So 2 to the 2 to the 2 to the 2k times, you know, that's an example of a highly compressible string, yet it's massive, it's huge. So the function drops.
Is the neighbor of a compressible string also a compressible string?
Good guess. That would be a great question. My number of questions is blowing. I thought when I started this course, I'm like, oh, it's going to be hard to come up with good questions. I'm going to have to look at the textbooks to come up with the questions. But then you guys ask great questions, so you've been a great model in terms of questions. And then I'm like, oh, I'll put this question so that it links, you know, the pieces of the courses that I'm being a bit fast. What you just asked
Probably true, right? Because
is a good question.
at first I thought, no, it can't be true. But then, yeah, you can just compute the compressible one and then add 1.
Yeah.
So
With a Y, right? Adita? With a
With the I.
with an I, sorry.
it's interesting. It's like a continuity condition.
Yeah. Okay. Adita and Will. This theorem. Will, you deserve the name because you got.
There's a Y after the T.
Aditya. Oh, thank you. Sorry. Aditya. But I still pronounce Aditya.
You can pronounce the ya also, like it's like a yes or a ya.
Aditya. Okay.
How do you pronounce it?
I say Aditya.
Aditya.
Yeah, Aditya. Yeah.
Yeah, it's somewhat continuous. The nearby terms cannot be dramatically large because of the argument you gave. If this is a simple number, its neighbor is also simple because you can get the neighbor by describing first this one and then say add 1. Great. Okay. Obviously now, okay, yeah. Now, there's another question from the problem sheet that I ask. Question 7. I ask to show that it is upper semi-computable. Let me first say something. The function is uncomputable. There is no, and this is what I'm going to be doing next. There is no algorithm which can get as an input x and produce k of x. So the graph that I wrote down there here, I made it up. And no computer program can display it for me. No algorithm can display it for me or compute it for me. However, question 7 is I ask you to show that it is upper semi-computable. Upper semi-computable, which means that you can have a never-ending algorithm which is going to find ever better upper bounds. So you can have a never-ending algorithm which is going to go like, that's an upper bound for k of x hat, with x hat being here. and then it's going to produce another one. That's an upper bound for that value. That's an upper bound. Oops. That's an upper bound for that value. That's an upper bound for that value. Oh, I've got a better upper bound for x hat. That's an upper bound for that value. Oh, I've got a better upper bound for that value. Okay, I'm gonna stop. But so the algorithm never stops. Unlike me, he never gets bored of doing it. And he just marks green dot. Green dot. It might be the first time he puts a green dot. It would be his first upper bound for a specific value. Or it might eventually update its upper bound by another point, which is going to sit closer to the graph of k of x. So upper semi-compute the function means that the never-ending algorithms come up with ever better upper bounds of the graph. And its tentative upper bounds, they converge to the graph in the limit of infinite time. So if we look at what happens to that algorithm at infinite time, the set of green points will coincide with the black points. So the upper bounds are going to go lower and lower and lower and lower, and they're going to espouse the function. Eventually, they're going to converge to the function, eventually, at the limit of infinite time. That's what it means for a function to be upper semi-computed. To help you in solving problem 7, we will see a number that can be lower semi-computed. And we're going to work it out. So you're going to see how things can be done. So that function I claim is uncomputable, but it is lower semi-computable. We can semi-compute it by above in the limit of infinite time. Are there any questions? Theorem. The function x maps to k of x is uncomputable. This is what we will do after the break. Let's reconvene at half past. Okay. The function k of x is uncomputable. That's our theorem. Proof. Usually the trick is to suppose that it is. So, assume that there is a Turing machine M that computes that on input X computes K of X. Now consider the following program. Simulate M to compute k of x for x equals 1, 2, 3, and so on. Until some ZB is found. ZB is just the name of a number. Eventually I'm going to find ZB. It's found for which? What is ZB? Well, it's a string such that its complexity, ZB, the complexity of the string ZB is strictly larger than B, where B is some number that we will come back to. Output that ZB. Okay, so let me help you process. We assume that the function is computable. That means there's an algorithm that on input x can compute k of x and halt. We're going to, I called it the Turing machine M. So we use M to compute k of 1, k of 2, k of 3, k of 5, k of 4, k of 5, and so on. Until, let's fix our minds, suppose that b is equal to 10 to the 10. Until we find the first string whose complexity is larger than 10 to the 10. We output that string. Right? 1 has complexity smaller than 10 to the 10, so k of 1, I don't know what it is, but M will tell me, and will tell me k of 1. It's going to be smaller than 10 to the 10, so most likely I'll have to go to 2, to 3, to 4. Eventually I might hit a string of length, roughly 10 to the 10, a random string, that has complexity larger than 10 to the 10. That's my number b. Right? Like now to be sort of intuitive to help you process it, I have fixed b to 10 to the 10. So I am outputting the first string who's in lexicographical order, whose complexity is larger than my threshold b. I will come back to b, to fix b. But for now, let us investigate what's the length of this program. M is of constant size. It involves, whatever is the subroutine to define M, the algorithm of M. I use it here as a subroutine. But M is of constant size. There's B. I need to give B in my program, right? Letting x run over increasing values, that is of constant size. I'm not specifying what is x. X is sort of a dummy variable. ZB is defined as the first string in this increasing order, or the first number, which will have complexity larger than B, but my program needs to know B. So the hard coding of the constant b can be given in a self-delimiting way by 2 log b plus 1 bits. And the rest is constant size. So the size of the program is 2 times log b plus some constant c. This is where now we fix b. Let b be any number such that two log b plus c is strictly smaller than b. Okay, so what is c, what is b? B is supposed to be a constant, but then I'm taking the log. Let me unravel a little bit. I'm building this proof. I said think of b as being 10 to the 10. So let's set up b to be 10 to the 10 in our mind. What's the size of the program? There's constant size to invoke m. There's constant size to invoke what we need to do, which is to compute k of 1, k of 2, k of 3, up until we find some number whose complexity is larger than 10 to the 10. Oh, hang on, I have to give 10 to the 10 in the program. To give 10 to the 10 in the program requires 2 log 10 to the 10. Because this number here will be hard-coded. And then what I want is to fix b, any solution to that. And by the way, this will, there's like only a finite numbers of b when b is small. Will I have that this quantity here is smaller than that quantity here? When b gets bigger, this will hold. So for example, if c is greater than 8, then setting b equals 2c works. Because this equation will be fulfilled. I wrote in my notes that, but I didn't write the explanation. So I either have to compute it with you, or for you to take it for granted, Why is that? If c is greater than 8, then what is it? 2 log of 2c plus c is smaller or equal to 2c. And c is greater than 8.
Feels like it would need something like C is lesser than something.
Sorry? It would need?
I don't. We can go ahead. Like I thought it would need something like C is lesser than something for this to hold, because if you can make C really large, you can make this equation not hold. Right? Because like if C is very large,
Yeah.
I can choose a B for which this will not hold, but whereas if C is sufficiently small.
Yeah, but c is also here.
Alright.
Yeah, so
Okay.
I would prefer not to go into these details, but I mean, the moral of the story is that there's a finite number. If you go like, oh, b is equal to 1, then this equation does not hold. Right? Because, hang on. Oh, yeah. Because you have like log of 0, basically you have c is smaller than 1. No, it doesn't work. If b is equal to 2, it may not hold again. But eventually you're comparing something that grows like log and has a constant head, it has a constant start, with something that grows like linearly. So all these values of b will do the job. Okay, so you just choose one of those b. Let b be any number such that this holds. Now I have in my notes that this holds, but I don't want to verify it. You can check it for you. It's the kind of thing that if I do on the whiteboard, it gets confusing. I might have been wrong, by the way, but it's sure that there are all values of b except a finite number. This equation holds. Just pick one. And now what do we have? So what do we have? We have a program of size 2 log b plus c, which produces zb. Thus, we have a program of size 2 log b plus c, 2 log b plus c, which is strictly smaller than b. So I'll just say we have a program of size strictly smaller than b. That produces zb, or which produces zb. However, zb has algorithmic complexity strictly larger than b. Contradiction. Let me help you process it. I think that the appearance of the b and the constants render this proof a bit cryptic, but in fact it's not so cryptic. In green, I'll basically make an example. I said suppose b is 10 to the 10. Great. Simulating m computing k of x for x equals 1, 2, 3, until some number is found such that k of z is larger than 10 to the 10. All that, suppose that all that has, so the size of my constant here, everything except hard coding b, suppose it's 1,000,000 bit, 10 to the 6. Okay, so I have 1,000,000 bit to write down the program, simulating. Well, I'm supposing that m computes the function k of x. So that is a program in itself, smaller than 1,000,000 bit. And then I'm embedding those, it's a very small amount of routines. Just basically use m to compute k of 1, k of 2, and so on. Now, if b is 10 to the 10, 10 to the 10 is 1, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8. That's 10 to the 10. Okay, so b bar, its length is going to be 21. Right? B bar is the self-delimiting encoding of b. I will need 10 ones to say what's the length of 10 to the 10. Oh, in fact, okay, modulo like extremely small details, but 10 to the 10 encoding as a string. Let me just say that b bar has length 21. Okay, so my total program, I've got 1,000,000 bit to describe m, to describe my routine, and I've used 21 bits to describe 10 to the 10 self-delimitingly. So my total program, total length of the program is 1,021,000. Okay, 1,000,000 bit for constant size routine, 21 bit to encode 10 to the 10 self-delimitingly. I'm cheating because I'm using base 10 instead of bits, but this is where I don't want to get into those details. However, what I have done with a program of size just 1,000,000 bit, I have produced a string whose complexity is larger than 10 to the 10. I have produced a string whose shortest program is supposed to be 10 to the 10 bits, but I've just displayed a 1,000,000 bit long program for it. This is the contradiction. And yeah, so the assumption that we made that there exists a constant size program which computes x, which computes k of x for all x, cannot hold. Does this argument ring a bell? Does it sound a little familiar? Something we've seen long ago.
In the very beginning, we had the smallest number that is not expressible in 20 syllables or something like that. That's like basically the same idea.
Spot on! Look at that! We've produced the smallest number. This is the first one that appears in this list. 1, 2, 3, 4. So whenever we find it, it's going to be the smallest one, which cannot be expressed by a program of b bits or less. And in the first course, we saw Berry paradox. The smallest number which cannot be described by 20 syllables or less. Berry's paradox was that the fact that I've expressed it this way was a description in 19 or 18 syllables. Now the fact that we describe z this way, we're basically hacking the algorithmic complexity to have a shorter description of zb, which is supposed to be. This is exactly, produced the smallest number which cannot be produced by less than 20 syllables. Or by less than, a program less than b bits. And you run into a contradiction. So let me just connect with Berry's paradox in a bit more details. This proof is the formalization of the Berry paradox. In the first course, we defined, I called it K0, but let me call it K20. K20 as the smallest number that cannot be described by 20, oops, I'm gonna write it in English. Syllables or less. And the problem was that K20 was the smallest number that cannot be described by 20 syllables or less. I got 19 this time. I've described it by 19 syllables. Now, with the with a bit of all the work that we've done with computation theory, we can say, what do we mean by described? Is that a description? Maybe it is, but how can I do something with this description? Can I use it as an algorithmic description? Can I use this as a description that I can run on a computer program? So I think I finished the first lecture by saying, yeah, there's ambiguity in what we mean by described. Here, just for a parallel, ZB here, the proof involves ZB. The smallest number who cannot be computed, or that cannot by a program of B bits or less. Right? By demanding that the complexity of ZB is larger than B, it means that its shortest program is larger than B. It means that no program of B bits or less can compute ZB. And it's the smallest one. It's exactly, well, if you copycat it, there's profound analogy. The smallest number that cannot be described by 20 syllables or less. These are description perhaps in English and so on. Now, if we look at algorithmic descriptions, ZB is the smallest number that cannot be computed by a program of B bits or less. Now, it looks like that's a program. of b bits or less. This is the essence of the proof. It looks like I've got a program for b bits or less. But this program works on the assumption that one can compute the function k of x. So a resolution of the Berry paradox is to say basically that this is a description in the world of mathematics. ZB is well defined. But one cannot hope to use this description algorithmically as a program to compute ZB. Right? As I say, ZB mathematically, if you don't like to define a number in terms of words like that, ZB is the minimum over all x, such that, well, x is a bit string or a number, doesn't really matter, 0, 1, star, and k of x is larger than b. It's mathematically well defined, but yeah, as I said, we cannot use this program as a valid program. Well, precisely because the function k of x is uncomputable. We use it as a contradiction, basically. Are there any questions? Okay. Let me move on to a next section. I think I'm gonna go back up. Can I erase? The halting probability. Omega. So we met it last time. Now we're going to elaborate a bit more on it. Reminder. U of P is equal to Ti of J. That's the universal Turing machine. We're in the self-delimiting context. On input P is going to do the calculation of the Turing machine number I on input J, where P is equal to I bar J. we defined the Turing's number, chi. Let me just write it once here so that it becomes clear. Chi is equal to chi1, no, chi0, chi1, chi2, dot, dot, dot. It's an infinite, well, it's a number whose binary expansion is infinite. And the bits of chi are defined like that. Chi p, the pth bit of chi, is equal to 1 if ti of j halts, and 0 if ti of j loops. Now what's p? Well, p is given by that. The encoding of ij. And so another way to view chi is like this way. Using here this equation, if u is equal to 1 if u of p halts, and 0 if u of p loops. I'm basically, instead of defining chi now via the halting problem of Turing machine number I on input j, well, precisely because the universal machine on input p is, labeling those I and j, we can think of chi as telling us, yeah, does a program p halt or loop on input, on the universal Turing machine. Okay. Observe that the first 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus plus 2 to the n equals 2 to the n plus 1 minus 1 bits of chi encode the halting problem for all programs of length smaller than n. Okay, why? There's a 2 to the 0 program of length 0. There's 2 to the 1 programs of length 1. There's 2 to the 2 programs of length 2. And so there's 2 to the n plus 1 minus 1 programs of length smaller or equal to n. If you are given that amount of bits of chi, well, you can decide by looking at the value 1 or 0 if u of p halt or u of p loops. For all programs, for all p of length smaller than n. Okay. Now we defined last time omega as the sum over all programs such that u of p halts of 2 to the minus length of the program. Now we said it was the halting probability. If we put a monkey in a typewriter who we conjecture it has a chance 1/2 of typing a 0 and a chance 1/2 of typing a 1. Sorry, a monkey on a universal computer. Well then with probability 1/2 it will put a 0 and then the reading head will move or will not move or will loop. But the chance that he types a program that terminates is precisely given by that. Okay, so let me state our first proposition. Omega is a compressed version of chi, namely n bits of omega are enough to compute two to the n plus 1 minus 1 bits of chi. Or in the notation that I like using, if one is given omega n, well then there's a constant size program, definitely not time. The time is going to be ridiculously large. There's a constant size program which says, okay, I've got this by the way, this is, omega 1, omega 2, omega 3, omega n. It's the first n bits of omega. I denote them as omega bracket n.
And it should be like 0 point omega 1, 2, so on, right? Because we know it's a number between 0 and 1.
Yeah. Yes, let's do that. Did I do chi like that? Oh, well, for omega it matters. It's a good point. For chi it doesn't matter. Yeah, for omega it matters because we're summing things, so we really had a number. And yeah, let's define omega n like that. So it's, you take omega, it's binary expansion, and you truncate it to the first n bits. And so from omega n, with a constant size program, one can produce the output chi 2 to the n plus 1 minus 1. So I can't remember where I've read that, probably in one of the papers I read a while ago, but if chi is a piece of coal, then omega is a diamond. It really is a compressed version of the halting problem. You know, the whole point of coming up with chi was that we were encoding the halting problem into a number. Now what this theorem states us or tells us is that that number is, in the end, is very redundant. Because one can compute exponentially many bits of that number, so exponentially in n, with only n bits of advice, the first n bits of omega. Okay. It's time to stop. It's perfect time to stop. So we're going to prove this next time, and we're going to move on with some other results regarding omega, like the fact that it's random, it's algorithmically random, it cannot be more compressed, and the fact that it encodes some mathematical truths in its very first bits. See you next time.